Hello everyone. Last class we had discussed on 2 watt meter method. Now under this we'll be having one more part, that is balanced load. Now the load is said to be balanced when the impedance of the three phases are equal, and the supply is said to be balanced if the three voltages are equal and are displaced by 120 degree with respect to one another. Saying that you have three phases. So we have three phases, they have equal magnitude and they are differing by angle 120 degree with respect to one another. Because of which the current flowing through them through the three-phase supply will be also equal in magnitude and also displaced by 120 degree with respect to each other or one another. As the voltage will have the same magnitude and they are displacing by 120 degree, with this the current will also have the same magnitude, also they are going to displace by 120 degree with respect to one another. It is a balanced load. The wattmeter connections to measure the power in three-phase balanced circuit is as shown in the figure. So basically this is a star connection and these are the three phases. Now there are only 2 wattmeters which are connected for a three-phase supply. There is a possibility that we can connect 3 individual single-phase wattmeters to each of the line, phase A, phase B, phase C, to measure the three-phase power. But it is sufficient to measure three-phase power by just 2 wattmeters. Okay, so now W1 is the reading which is given by voltage across its potential coil. Now first of all, the wattmeter consists of 2 coils: current coil, potential coil. Current coil is in series. Potential coil is the potential coil which is connected across the load or the supply. Right. Now this potential coil is from point A to point B, that is from phase A to phase B. So voltage across its potential coil is what? It is EAB. So this is line voltage EAB. Current through the current coil. Current through the current coil is what? It is IA. So it is IA. Cos of, that is cosine angle between the voltage and the current. Cos of EAB and IA. Similarly, W2. W2 is what? It is the voltage. What is the voltage across this potential coil is ECB. That is from C to B. There is a potential coil. Right. Now, what will be the current through its current coil? It is IC. It is IC, which is into cos of ECB and IA. Now, the angle between EAB and IA, ECB and IC can be found by a vector diagram. Here, your line voltage EAB is equal to EAN minus EBN by star connection. In between these two phases, these two line voltage, we have two phases. Now between these two line voltage, that is between ECB is a line voltage. So ECB is equal to ECN minus EBN. This is very important. As I said, EAB is equal to EAN minus EBN. ECB is equal to ECN minus EBN. So we have to draw 3 vector diagrams. So this is there are 3 phases, right? EAN, EBN, ECN. All 3 are differing by an angle 120 degree now. Now assuming the load to be inductive. When you say inductive loads are the loads which are using in our home appliances, right? So it's a pure inductance. What is the condition for pure inductance? The current IA or the current always lags the voltage one angle phi or an angle pi by 2. So if we assume that the load to be inductive, current IA lags EAN. So here the current IA is going to lag EAN by angle phi. This is small angle phi. And also the current IC is going to lag ECN. This is ECN. Right. Therefore, now what is the angle between EAB and IA? So as I said, this whole part is 120 degree. Right. And you are dividing this 120 by 2 parts. So this EBN is coming here. This is negative EBN. So this will become 60. This will become 60 now. Right. Now again you are dividing this 60 into 2 parts. This will become 30 this will become 30, right? So as I said, angle the current lags the EN by an angle 5. So what is the angle between EAB and IA? It is 30 minus 5. Similarly, the angle between ECB and IC is 30 plus 5. So W1 is equal to EAB and IA are the line voltage and the line current. Therefore, W1 is equal to ELIL cos of 30 minus 5. W2 is equal to ELIL cos 30 plus 5. EAB, IA, ECB, IC are the line voltages and line current respectively. Now we need to add 1 and 2. So W1 plus W2, which is equal to ELIL cos of 30 minus 5 plus ELIL cos of 30 plus 5. So apply cos of A minus B, cos of A plus B. You get ELIL 2 cos 30 into cos 5. What is cos 30? Root 3 by 2. ELIL into 2 into root 3 by 2 into cos 5. 2 get cancelled. The answer remains root 3 ELIL cos 5. So this is the power measured by a 2 wattmeter for a star connection. So 2 wattmeters are sufficient to measure a 3-phase power. That is why we are using W1 plus W2, which is root 3 ELIL cos 5. Now we'll be looking at expression for power factor, which is W1 minus W2. So again, W1 is what? ELIL cos of 30 minus 5 minus ELIL cos of 30 plus 5. You're taking ELIL as a common. You get cos 30 minus 5 minus of cos 30 plus 5. Again, you apply cos of A minus B, cos of A plus B. You get ELIL bracket 2 into sin 30 sin 5. Sin 30 is what? 1 by 2. 2 get cancelled. Sin 5 remain. So W1 minus W2 is ELIL sin 5. Now divide this 4 by equation 3. So W1 minus W2 divided by W1 plus W2. We get ELIL sin 5 divided by root 3 ELIL cos 5. We cancel EL. So we get sin 5 by cos 5 is what? Tan 5. Tan 5 by root 3. So what is tan phi now? Tan phi is equal to, you are sending that root 3 to the LHS. You get root 3 into W1 minus W2 divided by W1 plus W2. Now what is phi? You take tan to the RHS, tan inverse of root 3 W1 minus W2 divided by W1 plus W2. Now the power factor is given by what? Cos phi. But what is phi? Phi is cos of tan inverse root 3 W1 minus W2 divided by W1 plus W2. So this is the final answer. Let's look at some numericals on 2 wattmeter method now. A 3-phase 400 volt motor takes an input of 40 kilowatt at 0.45 power factor lag. Find the reading of each of the 2 single phase wattmeters connected to measure the input. So a motor is been supplied by 3-phase 400 volt. It takes an input power of 40 kilowatt. Now we need to find the readings of each of the 2 single phase wattmeters which are connected to measure the input. Now, therefore, the total input power taken by the motor is 40 kilowatt. It is the combination of 2 wattmeters only, as we are using 2 wattmeter method. So W1 plus W2 is 40 kilowatt. The power factor is 0.45. By this formula of 2 wattmeter method, start substituting the value. Cos phi is what? 0.45. W1 minus W2 will remain as it is. W1 plus W2 is 40. You take cos to the LHS, it becomes cos inverse of 0.45. This will remain as it is. Cos inverse of 0.45 is 63.25 degree. Again, this will remain the same. You are sending tan towards to the LHS. It will become tan of 63.25. Again, the bracket will expression will remain the same. So tan 63.25 is 1.98. So this is root 3 W1 minus W2 divided by 40. So in order to get this expression W1 minus W2, it is 40 into 1.98 divided by root 3, where the answer is 45.72. Now we need to solve these 2 equations. When we solve these 2 equations, then only we can find the individual value of W1 and W2. Right? So how do you calculate this in a calculator? We have 2 equations and 2 unknowns, that is W1 and W2. So for this, I am using a calculator 100 ms. So press mode till you get equation 1. as we have two unknowns, press 2. So this is A1, B1, C1, and this would act as A2, B2, C2. So your A1 value is 1 equal to B2, B1 is 1, C1 is 40. A2 is 1 again, B2 is minus 1, C2 is 45.72. So you get the answer as W1 as 42.86. You are getting the answer as W1 as 42.86 and W2 as minus 2.86. If you subtract these two values, W1 and W2, you are going to get the answer as 40 kilowatt. So we wanted to know the readings of each of the two single phase wattmeters. So in the similar way, wherever there is a question that we need to find the readings of the two wattmeters, you are going to use this method which is in calculator to calculate the equations, two unknowns, right? Or you can do it manually also, no problem. If readings of the two wattmeters in a three-phase balanced load are 836 and 224 watt. Now, there is a three-phase balanced load. To that, there are two wattmeters. Its readings are 836 watt and 224 watt. So this is a former reader, this is a later reader. In the sense, it is W1, this is W2. So W2 is the later reading being obtained, which is obtained after the reversal of the current coil connection, right? Therefore, this W2 will become negative. Why? Because the current coil direction has been reversed. Calculate the power and the power factor of the load. So how do you calculate the power? That is the total power. How do you calculate power? Power is measured by using a wattmeter. So how many wattmeters are connected? 2. Right. So W1 is 836 watt, W2 is minus 224 watt. So W1 plus W2 is 836 minus 224, which will give me the answer as 612 watt. Now, by the formula of power factor, cos phi is equal to cos of tan inverse root 3 W1 minus W2 divided by W1 plus W2. Substitute the value of W1 and W2. W1 is 836 minus 224, which will become plus. Here 836 minus 224. So the numerator is 1060, denominator is 612. When you divide this, you get the answer as 1.732. Now multiply this root 3 into 1.732, you get the answer as 2.999. Tan inverse of 2.999 is 71.55. Therefore, cos of this is 0.316, which is the power factor of the load. We'll look at one more problem, which is again similar kind of this, and easier one. Now, each of the two wattmeters connected to measure the input to a three-phase circuit reads 20 kilowatt. So there are two wattmeters which are connected to the input of a three-phase circuit, which reads 20 kilowatt. Each of the two wattmeters. So each wattmeter is going to read 20 kilowatt. That is W1 is 20 kilowatt, W2 is 20 kilowatt. What does each instrument reads when the power factor is 0.866 lagging? With the total three-phase power remaining unchanged in the altered conditions. So here, each wattmeter is reading 20 kilowatt. Now, what will be its reading when the power factor is 0.866 when there is no change in the condition? Right. So W1 plus W2, 20 plus 20, which gives me 40 kilowatt. Power factor is 0.866 as usual by the formula of 2 wattmeter. Here, you are substituting power factor as 0.866. W1 minus W2 is as it is. W1 plus W2 is 40. Cos inverse of 0.866. This will remain as it is. This is 30. Again, this expression will remain the same. You are taking tan inverse to the LHS. This will become tan 30 equal to root 3 W1 minus W2 divided by 40. So this is 0.577 with the same expression. So if you want W1 minus W2, it is 40 into 0.577 divided by root 3, which gives me answer as 13.325 kilowatt. Now when you solve these two equations, W1 and W2, as by the same method in the calculator, you get W1 as 26.665 kilowatt and W2 as 13.335 kilowatt. So we have found the readings of each of the wattmeters when the power factor was 0.866. Hope you have understood the problems. If you have any doubt, you can contact me. Thank you.